Okay, now let's look at some generic examples. We want to determine whether the following series diverge, converge absolutely, or converge conditionally. Determine whether the following series diverge, converge absolutely, or converge conditionally. Okay. All right, that's what we want to do. That's what we're trying to figure out, and that's what we're looking at. Okay, so here's our first one. We have k goes from 1 to infinity of negative 1 to the k plus 1 over the square root of k. All right. So anytime you have an alternating series, the very first course of action you do is take the absolute value of it. All right, because if it does, then that's absolute convergence. Well, let's try that out. So if we take the absolute value of this, then we get the series. K goes from 1 to infinity of 1, because that negative is now taken out, over, and I'm going to write this as k to the 1/2, because now I can see this for what it is. With this series, I know that my p is equal to 1/2, which is less than 1. So what does that tell you about the p series? Diverges. But if it diverges by the p series, now check the alternating series test, because it could conditionally converge. All right, okay, so we've got two criteria that have to be met. Criteria number 1, non-increasing, right? I have a sub k is equal to 1 over k to the 1/2. Well, yeah, the denominator is growing. It's the only one with the variable in it. Yes. Denominator grows faster than the numerator. Okey-doke. And then take your limit of 1 over k to the 1/2. We know that equals 0, so yahoo, that works also. So if the alternating series test holds true, now we're looking at this, then the series converges conditionally. All right, so you don't have to say, and this one by some test, because it's conditional convergence. So then this, I should write here, converges by the alternating series test, right? So I know that's what tells me I have conditional convergence. All right, so you have absolute convergence, conditional convergence, because we actually did 2 tests on this one. We did the p series test for the absolute, that diverged, which means we went into the alternating series test, and that's why we have conditional convergence. All right, let's do another one. So we got a few that we're going to go, let's just do a whole new page. We got a few that we're going to go through here just so that we can practice this a little bit. The series from 1 to infinity of negative 1 to the k plus 1 over the square root of k cubed. So absolute convergence implies convergence, so you always want to go there first. So absolute value, this little fella. Absolute value. And honestly, guys, I totally know you can do the majority of these kinds of things in your head. The whole purpose of these series tests is to show the proof, right? So a lot of these series tests, you can do a lot of them in your head. Not the integral one, but definitely the divergence one. But then you have to show the limit, right? Definitely some of these other ones you can do in your head. Like here, you automatically know that this is going to be converging by the p series. I mean, you know that. You know this is going to happen. It's just a matter of writing down the work to make it so. It's a proof. So I now have 1 over k to the 3/2. Oh, what do you see? P series. P is equal to 3/2, which we know is greater than 1. What do you know about that? Converges by the P series. So absolute convergence implies convergence, which now means the series converges absolutely. Some of them are not quite so obvious, right? So we don't always have this super obvious thing that we're looking at, but these are, like if you have the P series, those are super obvious. So you can just pull that stuff off, but good. Good. Okay, let's do another one. I mean, literally, we're just going to practice a couple of these because I want you to see a couple different scenarios. Over here, we saw the conditional convergence. Here we have absolute convergence. Look, this is all just P series, P series. Well, what happens if we need to figure this out that's not necessarily a P series? Well, let's take a look at this one. If I have my series going from 1 to infinity of the sine of k over k squared, right? All right. So if I have the sine of k, well, that's just not a super common. We're still going to do absolute convergence implies convergence. So let's absolute value this. What happens when I have sine? What does sine do? Yep, it jumps back and forth between +1 and -1, right? That's sine. But if I take the absolute value of sine, then what happens there? Yeah, we're going from 0 to 1. That's my absolute value, right? So if I'm looking at this, then if I want to this is not just a straight up P series. I can't just look at this. So I have to approach it a different way. So what do we know where we can use, what kind of test can we use some P series information and be able to attest? Okay. Okay. So I'm assuming you're talking to me. Do you see that? Comparison test, right? We want to compare what's going on with this. So if I do my comparison test, I have the absolute value, so a sub k is equal to the absolute value of sine of k over k squared. B sub k here will be 1 over k squared. And I know with my comparison test that the absolute value of the sine of k over k squared is definitely going to be less than or equal to 1 over k squared. What happens with my direct comparison test when I see that p is equal to 2, so this converges by the P series? What happens when my comparison here, this B sub k, is bigger? Because it's bigger and it converges both, therefore I know my original also converges, right? So absolute convergence implies convergence. So the series converges, and now I know that, oops, get rid of that little fella. My actual series going from 1 to infinity of sine k over k squared absolutely converges. This is by a comparison test. Because absolute convergence implies convergence, right? So I know that this absolutely converges because I'm showing convergence from the absolute. Now, it's a lot of these, we're going to show convergence with the P series. And if you can, that's super easy. But it doesn't have to be, right? I can still take this absolute value, use the comparison test, and come up with the fact that it converges. That's okay. You don't always have to do just the p-series test on these. It could be something else, and that's why I like doing this problem, because I feel like sometimes we get in a rut with that p-series because that's what most of them are. Okay, one more. One more, we got this. Example 3D. K is going from 1 to infinity of -1 to the k times k over k plus 1. Absolute convergence implies convergence, but what just happened? What do you see right now? What's our go-to test again? That's right, little divergence test action. If I'm looking at this and I take this limit, you get 1, which does not equal 0. Therefore, this diverges by the divergence test. Now, check it out. If this diverges by the divergence test, do I need to check for alternating series test? No, good, why not? What's the second criteria of alternating series test? That the limit goes to 0. If I'm looking at this particular problem, is my limit going to go to 0? No. So if it diverges by the divergence test, you're done, right? There's nothing else you can do. Therefore, the series diverges. Good. So if you're doing the divergence test, then you're finished. There's nothing else you can pull off from that. All right, cool. Alternating series test. Look at us building up our series tests.